Okay, let's go ahead and get started. It's my great pleasure to introduce Hiranya Peiris. She is a professor at the University College London, and she's also director of the Oskar Klein Center in Stockholm. Hiranya did her PhD at Princeton, where she was a key member of the WMAP team that made precision measurements of the cosmic microwave background. She and I then overlapped. We were both Hubble Fellows at the KICP in Chicago, and then she went on to UCL. Hiranya is known for working on a wide range of topics. She's worked on many topics in cosmology, from the CMB to supernova to large-scale structure. She told me recently that she's just started working on condensed matter techniques to probe axions. So she's really excited to have her here today to tell us about survey cosmology and what we can learn from it in the next generation. So thank you, Hiranya.
Thank you very much. Can you hear me in the back there? Perfect. Thanks very much for the invitation. It's been a great pleasure to visit. I haven't been back for a while, and yeah, it's wonderful to see so many familiar places. I'm going to talk to you about the era of surveys. So surveys are representative samples of the universe measured at different wavelengths, and now we're starting to do it also in terms of gravitational waves. And by measuring representative volumes of the universe, we can try to learn something about its origin, its evolution, and the underlying physics that drives that. If it's possible, could you just turn down the lights a little bit? If somebody is there to do that.
Maybe?
Yes. It's just that there are some pretty pictures.
Okay, so it depends. You may completely off.
Oh, no, not that one.
You may special, you may overhead.
That's good, that's great, that's great. Yes.
Good.
Thank you so much. Okay. So in this era of surveys, the cosmological implications of that has been founded on measurements of the cosmic microwave background. So our understanding of the standard model of cosmology is underpinned by measurements, which of course started in the 60s, but starting in the 1990s, we had satellite missions and also ground-based experiments, which measured the power spectrum of the cosmic microwave background to greater and greater precision. And that led to the establishment of a cosmological model, the parameters of which we can measure to very high precision nowadays. So this is the map of the cosmic microwave background temperature from Planck, which I'm sure you have seen many times. I wanted to contrast the evolution of the quality of the data from when I first started working on it. So this is, I looked in my notebooks recently and I found this picture. This is the first power spectrum of the WMAP data after the sky closed for the first time. So this is 6 months of data. And you can see all the scatter in the data. We were starting to fit models. The likelihood function was not perfect, so the specialists in the audience will see some problems various places. So, you know, this is data spanning the very largest scales we can measure in the universe to smaller scales. So contrast this with the Planck 2018 final data. This is the final data release of Planck. That's the temperature power spectrum. It's worth paying attention to the scales as I go through the next two plots. So this is the temperature. That's the scale is about 6,000 microkelvin squared there. And what you're seeing here are the error bars, including both the instrumental error and the cosmic variance. So at very large scales, the cosmic variance error dominates. But down here, at these very small scales, the error bar is so small that the dot is bigger than the error bar. Yeah? And when you fit a cosmological model to that, it goes through all of these points, and these are the residuals. Now, we can repeat this exercise with the temperature polarization cross spectrum. And now that's a smaller signal. It's still very well measured, but now you can start to see the error bars. And that's the residual with the cosmological model. And finally, this is the E-mode auto spectrum. It's a much smaller signal, and still it's very well measured, and you can see again the residuals. So this is a dramatic improvement in our precision of making measurements, and it also represents a radical data compression. So the Planck data, the raw data, the time stream of measuring the temperatures differences comes from about 2 quadrillion samples. You can compress that into 50 million pixels over 9 frequencies in terms of maps. Okay, I will try again. If all of the information here is Gaussian, and we can actually test the accuracy of that to extremely high precision, you can compress all the information in these maps into 2,500 multipoles. And all of that data is described very well by a model with 6 parameters. And that is a pretty amazing thing. So let's go into a bit more detail on these parameters. I don't want you to necessarily pay attention to all these little numbers here or anything like that. But it's a statement about precision. Most of these parameters are measured to % precision, and it's a model that consists of baryons, dark matter, some statement about how the universe was reionized, the power spectrum of initial conditions, and also assuming flatness and assuming that there's a dark energy component in the universe. And you need the amplitude fluctuation of the original power spectrum as well. And once you fit a model to that data, you can derive some other parameters. For example, you can derive the Hubble constant, the present expansion rate of the universe, which I will come back to later in my talk. But it's a derived parameter, and it's based on fitting a model in the early universe and using physics to extrapolate it forward in the evolution of the universe. Another thing you can see in this plot is different components of the Planck data and their relative constraining power. So if you pay attention just to the blue part, you can see very, very tight constraints. If you look at just the temperature, the constraining power worsens a bit. And if you just use these smaller signals to make measurements, you get bigger ellipses representing loss of constraining power. One of the really intriguing things about this particular plot, having also worked on WMAP, is that the Planck EE spectrum is roughly similar in constraining power to WMAP. That's the smallest signal that Planck can measure. So that's pretty cool if you're a CMB person. Something else that we can do with this data set is to check its internal consistency. So you can cut the data up into various different multipole ranges and various components in terms of temperature polarization combinations, independently fit the cosmological model to those, and see how much your parameter constraints change. And again, I don't want you to take a detailed point about this from here, but it will be relevant later in my talk, which is that the issue of systematics is very important in cosmology now. And we need to maybe do a lot more internal consistency checks of all of our data and our probes in order to make sure that the inference that we are making about physics is accurate. So, okay, so that's very great. We have made tremendous leaps forward in measurements. We have measured the parameters of a model extremely well, but unfortunately, it hasn't really illuminated some very deep questions about the components of that model. For example, if you look at the matter sector, 5% of the energy budget of the universe today is described by the standard model of particle physics. The rest we can infer through its gravitational effect, and much of it is dark matter, and also there's a very big slice here of the pie, dark energy. And on top of that, we need to understand where did all of the structure in the universe come from. So our dominant theory of that is inflation, and inflation makes a very good phenomenological fit to all of our data. But we have not yet detected a prediction of inflation in terms of primordial gravitational waves, so we can't say for sure that was the theory for the origin of structure. So in a kind of heuristic sense, okay, here is a model that has 3 ingredients: dark matter, dark energy, and the origin of structure or inflation, and these are all beyond the standard model of particle physics. It's new physics, and we do not understand the fundamental physical nature of those components. A colleague of mine says, you know, if you're writing down a model, you're allowed 1 tooth fairy. So in this model, there are 3 tooth fairies, and that makes one a little uncomfortable. So actually, following on from some conversations with a colleague earlier today, I decided to make this talk slightly more philosophical and reflect, what do we do when we have a standard model and the parameters of that model are measured to very high precision and we keep measuring it better and better and better, but there are ingredients in that model where we don't have a description in terms of fundamental physics that we can test in the lab or have detected in the lab, okay? So in that context, there are 2 possible paths to a paradigm shift, and this comes from John Wheeler, this characterization. One of the things you could do, he called conservative radicalism. So this is where, okay, you've got a set of principles that actually underpin your model. So the standard cosmological model is phenomenological. It assumes GR, it assumes broken time translation invariance, homogeneity and isotropy on very large scales, and a model for initial conditions, and some ingredients as well for the cosmic energy budget. Okay, so you can give up these principles, and you can do it one by one, okay, in a rigorous way, and you can explore the consequences of breaking those assumptions. So this must be done rigorously because principles are precious, and we don't want to end up in a situation we have a lot of epicycles. The other thing that you might want to do is called radical conservatism. So lambda CDA might have these ingredients that actually are, tooth fairies in some sense, but it's actually a very, very predictive model. So when you fit it in the very early universe for the CMB, you can make predictions for what you would observe in different data sets and at different redshifts in the evolution of the universe. And then you can go and test, whether you actually meet those predictions and whether it is testable and passes those tests in other regimes that you have not tested it yet. So if you keep doing this and you take the model seriously and explore its predictions, eventually it will break. And this is typically how paradigm shifts in physics have happened. So given that, probably for extremely fortunate reasons, we can't actually make universes in our lab and test this physics, this is a very good way to perhaps take the step of trying to work out what is underlying our phenomenological model of cosmology. And one obvious thing to do is to look in galaxy surveys. The initial conditions that we see and which we measure at the cosmic microwave background extrapolate forward in terms of gravitational evolution. And when you look at large surveys of galaxies, they reflect this initial structure through gravitational evolution. The galaxies are not distributed randomly. They follow patterns. They stretch out along filaments, and there is expected to be dark matter underlying those filaments. So this connection between dark matter and galaxies, very nice work is being done by Risa here on that connection, actually allows you to use galaxy surveys to probe the underlying dark matter distribution and how that evolves, which also tells you about dark energy and also about initial conditions. So when we look at galaxy surveys, we can also fit the same models that we fit in the CMB, and you can measure the same parameters that you measured in the CMB, and you can compare those things. This leads me to the idea of cosmic consistency. So again, this is something we do as cosmologists because we can't do experiments in the lab. Okay, so you're trying to measure the same thing, the same parameters with different data sets and see if under the assumption of a particular model, they agree. Here's an early exercise of doing this. It is one of the studies which hinted towards the existence of dark energy. So the particular parameters, etc., don't really matter. I find it fascinating to look at these plots and this is COBE, that's CMB data. This is the APM galaxy survey, and this is a velocity survey. And they're doing some version of what we would now do in terms of Markov chain Monte Carlo to explore likelihood surfaces and produce posteriors. They're just plotting how these constraints cross when you make those particular model assumptions. And you can see that when the Hubble parameter is a bit low and the cosmological constant is greater than 0, they start to cross. So this exercise has been done by cosmologists for a long time. This is a particularly beautiful example of it. This was in this paper following the discovery of the accelerated expansion of the universe. And on the left-hand side, there is a theory plot, and it shows cosmological constant density, matter density, and curvature density. These are different cosmological models, and these are what would happen to the universe and its curvature if those models were true. And on this side, there's the observational plot, where you see CMB constraints, constraints from clusters of galaxies, and supernovae. And again, this was a favored model of the past. This was a favored model of the past. I'm sure there are people in the audience who remember when those models reigned. But lambda CDM won. So that is a way to use different types of data sets and their consistency to try to work out how we got the parameters of the model right. So we can do this test with lambda CDM as well. So here's an example where it works. Okay? So what is shown here is the CMB lensing amplitude and its scale dependence. So the CMB, as it passes through the intervening large-scale structure, gets lensed and therefore carries information about the late-time evolution of the universe. And so if you fit a model to the primary CMB data, which doesn't contain that information, you get this black prediction. And then you go and measure the lensing amplitude, which is independent data. You see that the prediction matches that the data that's taken at different time in the history of the universe. So that's an example where the consistency succeeds. Here's another extremely impressive example. This is wave number spanning 3 decades in scale. And these are observables spanning about 14 gigayears in cosmic time. And this is the matter path spectrum predicted by Planck. And you can see down here, at very large scales, we have measurements from the CMB. And at smaller and smaller scales, you have multiple probes. Galaxy clustering, Lyman alpha forest, cosmic shear. These different data sets, these different probes actually overlap. So you can see if you've got a calibration error between them. And you can see that it's very consistent. It's a very nice result. The latest survey to start doing this exercise of combining self-consistently different probes of the late-time universe is the dark energy survey. There's a lot of involvement here at Stanford in that. I just wanted to show you this picture of the Blanco telescope. And I don't know if you can see that it's made up of lots of little pixels. Each pixel is a woman working in the dark energy survey, so yes. This is the latest public results from the dark energy survey doing what we now call multi-probe cosmology. Okay, let me explain this plot. I'm not showing this to say, oh my God, there's extreme precision from this and we rival the CMB. That's not the point of this plot. It is a proof of concept with 1 year of dark energy survey data. So here we have the matter density and the vacuum energy density. On this side, the dark energy equation of state. if you pay attention to the green, the very tight constraint, this is the old way of combining cosmological probes, where you take different experiments who have taken data in different ways and analyze them separately and produce a likelihood, and you just multiply those likelihoods together and you get a constraint. So this includes the CMB, supernovae, and spectroscopic baryon acoustic oscillation results, and they all come from different surveys. So what this misses is that it might get the statistical part right, but it may not necessarily get the systematics part right, and all of these probes are limited by systematics. So instead, the approach of a survey like the dark energy survey is to analyze all of these probes through the same quality control standards with consistent treatment of systematics and blinding, so that when you actually put a circle on these plots, you can trust its accuracy and not just its precision. Okay, so this is the first demonstration of that from dark energy survey. The constraints are still very broad, but that's a small fraction of the data. And it's using the so-called 3 times 2-point analysis, which includes cosmic shear, galaxy-galaxy lensing, and galaxy clustering, and also supernovae and photometric baryon acoustic oscillations. So we can start to get these constraints, and this will only improve into the future from the dark energy survey, stepping on to surveys like LSST, which I will come to later. Something else, kind of sociological, I wanted to point out, because it's very relevant these days, is that this is where people working on the dark energy survey come from all over the world, and they work together to get us results about the fundamental physics of our universe. And it seems like this kind of international collaboration is less and less appreciated in many countries, including this one. So I hope to be able to come back, with LSST and show you similar plots. Okay, so these things also impact our science. All right, so I mentioned systematics. Systematics is the current name of the game. So I like this quote: no one trusts the model except for the person who wrote it. Everyone trusts an observation except for the person who made it. If you make an observation, or even if you take some telescope data somebody else has taken and analyze it, often you really, really have to work very hard to convince yourself that you got it right. And when I come to the next part of my talk, which is about cosmic inconsistency, in other words, when you make kind of predictions for these consistency checks and it doesn't pass, you always have to have in your back of your mind, is this a sign of a breakdown of the cosmological model description, or is it actually a systematic effect? So in that spirit, let's look at one example which I personally find intriguing enough to put time into it. And that is this measurement of the local expansion rate of the universe, which is also called the Hubble constant. And here is one way to visualize the problem. Okay? So this is redshift, and here are measurements of the expansion rate. If you take the model fitted to the CMB at high redshift and extrapolate it forward, it's that black line versus the error bar is so small, it's a tiny, tiny gray band. Can you see it? Maybe. Okay, there's a little gray band here, and the error bar is that small, and it hits at about 67. If you measure the local expansion rate with the local distance ladder method, which I will come back to in a minute, you find that you get a measurement here. And this discrepancy is getting very intriguing. And why is it getting intriguing? It's because we believe the error bars and the systematics analysis of both of these data sets. There are many different ways to measure this quantity, but many of them are systematics dominated, and these two are the most trustable methods. So that's why this is intriguing. Let me go back to a little bit of history and definition for the Hubble constant in case there are undergraduates, etc. So observations in the 1920s showed that galaxies were moving away from us with their speed proportional to their distance. That was the discovery of the expansion of the universe, one of the most fundamental things the human race has ever done. And the Hubble constant is the constant of proportionality to find that the velocity and distance are related by this constant of proportionality. And it defines a time scale for the universe. So for example, if it's 70 in kilometers per second per megaparsec, that implies the universe has a time scale of about 14 gigayears. So how do you measure this? So you can estimate it in different ways. One is by measuring both the redshift and a distance to a single astronomical object. And that comes with caveats. It should be in the Hubble, now Hubble image flow. And its peculiar velocity can be measured. So peculiar velocity is local random motions that are there on top of the Hubble expansion. Or else that it's sufficiently distant that this peculiar velocity doesn't affect its redshift measurement. It should not be so distant so that the cosmological expansion dynamics enter into the data analysis, because then it becomes not a model-independent measurement, but an inference based on an underlying model that needs to be accounted for. It's difficult to find such a class of objects. So other options are needed. One of the things that we do is, of course, to use the cosmic microwave background. And that gives all the cosmological parameters. You have to make assumptions about choices of those parameters and the ranges over which they're allowed to vary. But once you make those assumptions, you can extrapolate that model forward and get the derived parameter, the Hubble constant. So that's indirect. And then the local, the distance ladder is also local but indirect. Okay? So you can measure distance to a nearby object, usually using parallax. And then you obtain the distance ratios to more distant objects in the Hubble flow. So you go step by step, you build rungs where you can cross-calibrate, you step out from Cepheids to supernovae, but you also need a redshift of the host galaxy. Again, since I'm showing old plots, I will show Hubble's plot where the expansion of the universe was discovered. If there are undergraduates in the audience, they will see that velocity has wrong units. So, you know, now from that time till today, here's a kind of another sociological plot. So you can see from the 1930s to 2015, when this figure was made, there's Hubble's wrong measurement up here. He refined it pretty rapidly. And these are the Hubble wars, which I'm too old to remember, where the Hubble constant was unknown by a factor of 2. It was settled somewhere in the middle. So when I came into the field, the Hubble constant was 72. And we thought that was done. We, stop measuring it now. We know what the answer is. And when WMAP data was first fitted to the CMB, there was a big error bar compared to now. But the center was somewhere around 72. So everything was fine. Okay, done and dusted. And then both the local distance ladder measurements and CMB data continued to improve. And eventually, about 5 years ago, basically, Planck came in with this low value with a small error bar. And Adam Rees and his team continued to measure a high value. Okay? So when this first came out, one camp would say, oh, Planck clearly has something more to be understood. And CMB people might say, okay, you guys have this and this and this and this systematic in your error budget. All right. So unfortunately, what's happened in the meantime is that everybody has gone and checked their error budgets and found new ways to account for or look for systematics. And these measurements still disagree. And then you start to wonder, is it still systematic? Is it some unknown astrophysics, perhaps? Or this is the thing that animates us all? Is it new physics? Is this a sign of new physics? So then, as we are wondering, we've got these two seemingly very precise and possibly also accurate measurements that tell us different things about the universe. So a new thing came into the game, which is the Abbe-Detol measurement of the Hubble constant from a single standard siren from a merger of binary neutron stars. So I'm going to now talk a little bit about that. So this is possibly a new independent probe to arbitrate this tension. You probably heard a ton of talks about it, but let me just briefly remind you. So when GW170817 was detected, it was first detected in gravitational waves. And then a GRB was detected about 2 seconds later. And then basically all wavelengths, astronomers competed to follow up these observations. And the gravitational waves implied that it was a binary neutron star. There was an afterglow detected, which gave a precise location that allowed you to identify the host galaxy and measure redshift to it. Okay. Gravitational wave data give a chirp mass and a luminosity distance, which is about 44 megaparsecs for that one object. And by taking a spectrum of the host galaxy and modeling the bulk flow towards the great attractor, you can get a redshift estimate, which is about redshift of 0.01. And once you have those two numbers, you can calculate the Hubble constant. It came out bang in the middle with a big error bar, but let me just keep going. Okay, so just to emphasize the two parts of that measurement. So these are the dimensional strains measured as a function of time, and the time dependence gives you the chirp mass, and the amplitudes, once that's measured, gives you the distance and the viewing angle to the merger plane. So that's one thing, that's a distance. And then once you see a counterpart in electromagnetic radiation and it appears as a transient, then you can work out what galaxy it's in. That is the kilonova accompanying the object. You can see that the initial localization from LIGO alone was this green band here. The fact that nothing was seen in Virgo gave a tighter localization. And then this is the gamma ray burst observation. And by seeing an optical transient, it's basically pinned down to one galaxy. All right, so that's the redshift part and the distance part. So as I briefly said earlier, there is a dependence on measuring the distance on the viewing angle to the merger plane. And it's quite a substantial degeneracy. So if you measure H0, there is this degeneracy with the viewing angle. And so for reference, this green band and the red band and the Planck measurement and the Rees measurement, local distance ladder, right? So there's no way this thing can currently discriminate between those two measurements. When you marginalize this degeneracy down, you get a very non-Gaussian looking posterior. And it kind of looks like this, all right? However, you know, this has promise because this is a very, very low systematics way of measuring the Hubble constant. And I like this movie, if it plays now, that came from this blog called Research in Progress, which some of the younger members of the audience might be familiar with. And it contrasts fast versus exact methods. So there's a pair of dogs that try to go through this hole. And the fast one gets there faster, but it hits a wall, and the other one can go in. Sorry, I just love that movie. But basically, our analog of that is this. It's precision versus accuracy. So, you know, you want to actually know what the right answer is, and you want to know it with small error bars. If we keep increasing our precision of measurement without focusing on, for example, systematic uncertainties, you get a precise measurement which is very biased, but you want to also go down to the right answer and get accuracy. So you want to get an unbiased, precise measurement. And this is what this new probe has a potential to give you. This is the only technical part of the talk, but let me try to explain it. So what we wanted to do was to work out in detail how many of these objects would you need to get before you could arbitrate those two tensions and do it in a way that controls systematics. To do that, because as you saw, the waveforms are very, very complex, right? And the posteriors that you get out of that are also complex. And there's all sorts of calibration parameters to marginalize over as well. So they result in these very complex posteriors for the distance. In order to get them, we simulated these binary neutron star mergers. And we assumed that you got a host counterpart. That's a completely other kettle of fish, which I'm going to come to later. So this is a hard problem, but imagine that you did get a redshift, okay? So that means you are left with the distance. And so for that, we assumed 4 years of LIGO work operation. We assumed a rate for the generation of these events, which is compatible with current data. The waveforms were injected with colored noise, and we analyzed it the same way that LIGO analyzes the real data. This is a very slow process. It takes about a few CPU weeks per object. We are working on faster ways to do this inference. So that's why we only have a small sample. But out of that sample, we found 51 detectable events that would pass their signal-to-noise thresholds and lead to an alert to a transient survey. So again, this is a bit of a movie. I would like you to pay attention to, first of all, this signal-to-noise plot. Okay, LIGO triggers when this thing is about 12, by the way, for reference. So what it's going to show is the signal-to-noise increasing. The waveforms will come individually on this side and combined in this side, okay? So, let's see. Right. So this is a sample that's drawn from an underlying distribution, so it has sample variance as well. This is the underlying value of H0 in the simulation, and with this sample of 51, you get this measurement, which is precise, and it's scattered a little bit from the underlying value, as expected. So it turned out that, I don't have the detailed results in this talk, but it turned out that this 51 event sample was enough to arbitrate between the Planck and local distance ladder measurement. So that's the kind of number that we're looking for. The other study that we did was to check if these H0 measurements are unbiased statistically. They are very low systematics, but there are some. There are several issues which could come in. An inaccurate redshift measurement, which is hard to imagine, but it could happen. Peculiar velocity, you have to either marginalize over it, or you have to estimate peculiar velocity. There are uncertainties there. And the other one is a selection effect, which is that the triggers come through gravitational wave signal to noise on the observed signal to noise. And that sort of leads to a Malmquist bias type selection effect, which has to be accounted for in the analysis, because otherwise you get a biased estimate of the Hubble parameter. So this is essentially a study that showed as a function of the sample size, first of all, what the sample variance was, which is this variance here, and also the fact that it is unbiased. And so these are the Planck and local distance ladder measurements. So, for example, if you have a sample size of 100, you might both arbitrate between them and do it with minimal sample variance as well. So now I'm going to turn to the possibility of finding these kilonova observable counterparts of gravitational waves. And I'm going to do that by going through my favorite survey, LSST, which SLAC has a huge investment in. So it is a wide, that's half the sky, deep in terms of magnitude, and fast. It will image the whole southern sky roughly every 3 days. So that's wide, fast, deep, usually it's called. And it will begin in a couple of years. And it will survey the sky for 10 years in that mode. And again, it involves scientists in 23 countries, including the US, Chile, and a ton of international partners. So it is a survey and it is an amazing survey. It will expand space-time volume 1,000 times over current surveys. And the thing that really excites me about LSST is its discovery potential. We are going to be looking at the sky in a mode we have not done before in this large-scale survey of breadth, depth, and time sampling the sky very quickly. So that leads to essentially a movie of the sky. And when you move into this way of looking at the sky, you're not really astronomers. You're more like, okay, astronomers at work. It's common beliefs. I never use a telescope. I personally never use a telescope. I never go near a telescope. I would very much like to go near LSST, but probably they would keep me away. I do look up, but some people don't. You know, they look at their computer, right? So ask not what data you need to do your science. Ask what science you can do with your data. So LSST is going to do a lot of science. It's very diverse. And it's going to do 4 science missions in parallel. The traditional dark matter, dark energy, multi-probe cosmology that I showed you starting off with DES will be pushed to incredible depths with LSST. It's going to make a movie of the universe, discovering new transients over time scales that we haven't systematically explored before. It's going to do an inventory of the solar system, for example, looking for near-Earth asteroids. And it's going to map the Milky Way and extend the work, very exciting work that has begun with Gaia in terms of understanding the structure of the Milky Way and also providing test beds for dark matter physics. So to place it in the context of other dark energy facilities, I had this slide, I think, when I started to get excited about the UK joining LSST and was kind of lobbying for it, so that was in 2013. It's very scary that now we have come really to the start of the survey. So for the astronomers in the audience, you might look at this plot and see there isn't much spectroscopy going on. So if you're writing white papers for Astro 2020, please think about that. But you know, it's there in the dark energy facilities. And the cosmologists working on LSST have congregated as the Dark Energy Science Collaboration, or DESC, not DES. And so this is a collaboration which brings together not just astronomers and cosmologists, but particle physicists, computer scientists, and statisticians, because of the interesting data analysis problem that is there on top of the interesting cosmology problem. And it is going to do wonderful things for dark energy science by measuring the nature of dark energy very well. But the thing that really, really excites me is actually the discovery potential, and particularly discovery potential for transients. So this is a plot that shows the characteristic time scales in days versus peak magnitude for various classes of transients. Often these have been found through pointed observations and not really in surveys, except for supernovae, for which there are surveys. And the phase space of these transients will be opened up to systematic exploration for the first time by LSST. So it turns out that in order to actually accomplish this science, you've got to design the survey strategy in a way that allows you to characterize the light curves of these objects as they change over time. And this turns out to be a very, very complicated balancing exercise between, for example, the needs of the static science, like weak lensing, and the needs of the solar system people to see asteroids that allowed to be characterized by measuring objects in 12-hour intervals as they cross the ecliptic, and the timescales from days to weeks that are needed for this kind of transient science. So recently we did this very big exercise of characterizing how different cadence strategies would impact different science cases. So these are 2 different cadence strategies. You can see this one is more chaotic than this one. So by doing this exercise, I personally learned you can get excited about anything, including these tiny details of how the telescope is going to scan the sky. And here's an example of such an exercise for transient science. All of these are different types of scanning strategies. And these are the number of different kinds of transients that you would actually detect if you were to do LSST with that scanning strategy. So the reason that I was particularly interested in this exercise was to see, can we serendipitously detect kilonovae, the counterparts, the optical counterparts of gravitational wave binary neutron star mergers. And it turns out that if you change the scanning strategy to something like this, which I won't go into details of, you can substantially increase the number of serendipitous kilonovae that you would see. And then you can imagine some innovative types of research programs. The usual mode, the one that I actually described to you, is that LIGO sees something, they trigger an alert and tell astronomers, look in this big area of the sky, and then you might see the transient. This is just scanning the sky for these counterparts, okay? And if you detect them, and an alert had not been triggered, you can actually go back in the LIGO database and look for waveforms compatible with binary neutron stars, and actually increase the signal to noise by combining the signal to noise of the gravitational wave detector and the optical detection. It gives you localization, it tells you where to look. So it turns out that by adopting this kind of scanning strategy, we can actually start to see past the horizon of LIGO A+, which has just been funded, and go into higher redshift ranges as well. So this is work in progress, where we're trying to make this science case concrete and see what it would take to couple this reverse trigger approach to analyzing and finding these binary neutron star mergers quicker. So very scarily, LSST is going to have first light in 2019. This is a picture of the telescope in October last year, I believe. And with that prospect of exciting new data and new approaches to understanding what is behind our very bizarre and mysterious phenomenological cosmological model, I will end there. Thank you.
Great, questions?
So when you show those plots, you're assuming some density of these transient objects that is to say you haven't yet seen. Yeah.
Okay, so we have seen one, right?
No, you've seen one, but,
yeah.
When you say how many of each kind you're going to see, it's based on a model of their...
Yes, that's right. So we have very good ideas about common transients like supernovae, so that's not a problem. They're rare supernovae, but still we have tons of examples of them, so you can estimate rates better. With the kilonovae, the rate is very uncertain. I think this simulation has about 1,000 per gigaparsec cube per year or something like that. That rate is still compatible with the LIGO, limits. There are neutron star neutron star black hole binaries as well, which have not been observed yet. We expect to find them at a lower rate. So you're completely right, the rate has been assumed. One of the things that you could do to improve this is to marginalize over the uncertainty in that rate. But one of these calculations is very expensive, so that's not done. There's an error bar that comes from Poisson uncertainty, though, which is much bigger than the uncertainty in the rate.
Yeah, so when you were talking about discrepancies within the CDM, you didn't talk about the axis of evil and the low quadrupoles at low L. Is that just because you don't put a lot of stock in that? I wrote a paper in 2010 showing that this is completely a statistical fluctuation. There's something that is intriguing, actually, that if I can go back all the way to the Planck plots, and I don't think this is new physics, but it is intriguing, okay, because it pulls the cosmological parameters. There is a
funny fluctuation at, well, no. Yes, there's a funny fluctuation here at very low L. It's hard to evaluate whether it's consistent with a statistical fluctuation. It is quite a major one. But because it's at low L and the cosmic variance dominates, it doesn't have a very strong influence, but it definitely does pull the cosmological parameters in different directions. So for a while, there was a confusion whether W map was consistent with Planck. Once you realize that it is, then there was a confusion whether if you cut the power spectrum at about 1,000 and just analyze this part, are the cosmological parameters from that part of the spectrum consistent with this higher tail? And the latest analysis we've done in Planck shows that that's statistically consistent, but that the pull is coming from that feature. So if you have a very interesting model of the early universe, for example, that explains other things as well, not just that feature, that could be an interesting prospect for new physics. Yes. It's hard to work out how to do a consistency check with other data. It's at very large scales.
Any questions from a student?
I'm very friendly, asking questions.
Nick.
So with respect to this anomaly that you just pointed out, so these error bars won't get smaller in the future with CMDS or anything with the cosmic variance.
That's right.
So is there any perspective on this being resolved, do you think?
Okay, so as I said, it's very hard to test with a consistency check. The one avenue is polarization. Polarization will definitely be improved by future experiments. I'm not sure about S4, how low it will go, but certainly you can improve on polarization. And once you make a model for that feature, for example, from an early universe model, you can then make a prediction for what the polarization should look like. And the transfer functions for this temperature and the polarization are different, so there's independent information there. So a statistical test is possible. But whether it would ever convince anyone about new physics is debatable, just because it's hard for that purpose, the reason that I just pointed out. Yeah.
So if you end up using the optical data to go further into the noise of those events,
yes.
Are there new systematics that you have to worry about?
Yes, there are. Viewing angle systematics. Just as I said, there's a selection effect that comes from gravitational wave signal to noise. There is a viewing angle dependence. There's one in the gravitational wave data. There's also one in the EM data. It's not fully quantified. And the reason it's not fully quantified is that it requires a very detailed model of the 3D geometry of the opacity that is there in gases or whatever after the merger. So people are just starting to do 3D simulations of this. But those simulations often end at milliseconds, and the optical kilonova comes from days in the future. So it requires a huge improvement in modeling, but people are thinking of doing that. So once you know the 3D geometry, you can make predictions about how the light curves would look depending on which way you look at it. It gives more blue or red emission, for example. So more work needs to be done. But if you're lucky, that selection effect is identical to the gravitational wave one.
And can you go to your last slide with the redshift distribution?
Mm-hmm. Tell me when to stop.
The question I have is, in that distribution, did you use any information we have from, not that one?
This one?
No, the one where you have the various different ways of, one of the very last ones.
Oh, okay. Here? Anyway, just ask a question.
Anyway,
yeah.
Did you include, one of the other candidate observation for those redshift distribution is short gamma ray bursts, which are neutron mergers. And they extend, it seems to be further redshift than
I see what
you're
you
showing.
mean.
So that information be useful?
Yes, I think you're completely right. In fact, we got the idea for this thing. We got the idea for doing this because back in the day, before anything was discovered, people had suggested this reverse triggering with gamma ray bursts. The reason that I think this would be better is because you will only ever really see gamma ray bursts in very specialized settings where they're beaming directly at you. Often you won't see the gamma ray bursts in one of these mergers. So you have to have a special orientation to see the gamma ray emission. But people have done that. In the past, they have proposed this mechanism, and there was actually a recent paper following up on that as well. So. That's right. It won't necessarily help the Hubble constant issue because as you go higher in redshift, you have to model the expansion history with a model, but it will actually help you measure the expansion rate as a function of redshift better.
One question. So, all in all, with supernova and Planck data are so well defined, and now Planck data probably are not going to change much. Then, how many years this may persist?
So I'm hoping that it will only persist as long as we get a sample of binary neutron star mergers and make a third measurement, which, first of all, there are three possibilities, right? Either it agrees with Planck, or it agrees with the local distance ladder measurement, or it gives a third value altogether. But this is a very, very precise and not systematics limited measurement. So eventually it's going to nail down the Hubble constant. Whatever that is, it's going to nail it down. And if there's still a discrepancy between Planck and that measurement, in my view, it would reveal either one of two things. One is our measurement of the sound horizon in the early universe is wrong. There's another energy component in the early universe we haven't put in, or else something's very weird about dark energy. But I don't actually believe the latter because there are many observations about the late time universe which agree with the growth of structure that comes from the Planck measurement. So I think there will be something interesting about the early universe. Regarding timescales, if we say we want 50, there's a recent paper by Dan Holt estimating that we would get 50 in about 6 years. I think maybe perhaps a bit more optimistic, a bit more pessimistic than that. I would say between 5 to 10 years because of the uncertainty in rates.
You do get some extradition from binary black holes and that statistical measurement.
The statistical measurement I'm not a fan of because it's systematics limited. There are many methods to measure H0 which are systematics limited where you can't get that down. And I think it's a nice idea, but I would rather wait and look for these kind of golden objects.
All right, let's thank Hiranya again. That's great. Yeah. Right there.